Every year, people consume billions of capsules of standard omega-3 supplements, yet systemic inflammation and cardiovascular disease remain the leading causes of death worldwide. When cardiologists and researchers review the data, large-scale clinical trials frequently show null results for these generic interventions. In clinical practice, physicians routinely see health-conscious patients who supplement every single day, but whose blood tests still reveal a state of severe cellular lipid imbalance. This creates a dangerous blind spot. Patients believe their daily capsule protects their heart, while their actual cellular architecture remains entirely compromised. If the required dosage of EPA and DHA is being ingested, we have to ask why it is failing to reach and integrate into the cell membrane. EPA, or eicosapentaenoic acid, and DHA, docosahexaenoic acid, are the primary structural marine fats required by the body. The failure lies not with the lipid itself, but in a fundamental breakdown of pharmacokinetics and molecular delivery. Once extracted from their natural marine source, standard fish oils completely lose their molecular stability. This introduces a mechanism known as lipid peroxidation. Isolated EPA and DHA are highly volatile fats that react rapidly when exposed to oxygen and normal body temperatures. Because of this volatility, these isolated lipids physically break down and oxidize in the digestive tract long before they can be utilized by human tissue. Instead of resolving cellular inflammation, these oxidized fats become toxic free radicals, actively damaging the surrounding environment. The human body's metabolic pathways recognize these oxidized molecules as cellular waste, entirely preventing them from crossing the cellular threshold. Supplementing with unprotected omega-3 is biologically counterproductive. Without a stabilized molecular transport mechanism, the lipids simply degrade in the gut. At the microscopic level, the body requires a strict ratio of essential fatty acids to construct functional cells. The two primary lipids have contrasting roles. Omega-6 drives necessary pro-inflammatory cascades for acute immune responses, while omega-3 resolves and neutralizes that inflammation to return the cell to baseline. This chart shows the ideal physiological ratio of omega-6 to omega-3, which sits at 3:1. However, the modern clinical average routinely exceeds 20:1. This violently skewed ratio physically alters the cell's membrane fluidity. Excess omega-6 packs tightly together, turning what should be a dynamic cellular wall into a rigid, deformed structure. A rigid membrane severely impedes basic biological functions. Essential nutrients fail to absorb, bouncing off the hardened surface, while cellular toxins become trapped inside. This hardening also blunts normal transmembrane receptor activity, crippling the cell's ability to communicate with the rest of the body. Chronic systemic disease is a direct structural consequence of this cellular rigidity caused by severe lipid imbalance. Since the market is saturated with generic supplements, we have to ask why this 20:1 ratio hasn't been corrected in the general population. The answer returns to molecular volatility. In nutritional science, the clinical viability of a lipid is measured by the Oil Stability Index, or OSI, which tracks how long an oil resists oxidation. Standard isolated fish oils have an extremely low OSI. Under normal gastrointestinal conditions, they break down completely in a matter of hours. Because they oxidize so rapidly, the body correctly identifies these degraded lipids as biological waste and immediately disposes of them. Attempting to fix the cellular ratio by taking larger doses of generic capsules fails. Gross intake cannot overcome a low oil stability index. Swallowing handfuls of standard supplements every day is biologically inefficient. True correction requires a structural change in the formulation itself, not simply higher volume. The solution requires looking at how marine omega-3s exist in nature. In a wild marine environment, these fats are never isolated. They are naturally bound to protective organic compounds. To mimic this natural stability, researchers developed an intervention that rebinds wild-caught fish oil with specific, highly potent polyphenols. Polyphenols are naturally occurring micronutrients packed with antioxidants. The specific protective agents used for this binding process are derived exclusively from pre-harvest extra virgin olive oil. Achieving clinical efficacy requires high-concentration lipid doses, and these doses must be scientifically documented to ensure they remain intact from ingestion to cellular delivery. The formulation integrates high levels of these specific polyphenols to act as a sacrificial antioxidant shield. The polyphenols take on the oxidative stress, ensuring the EPA and DHA remain fully bioavailable until they reach the cell. Shielded from oxidation, the intact lipids successfully integrate into the cell membrane, actively restoring fluidity and normal metabolic function. Firmly, polyphenol binding is not an optional enhancement. It is a non-negotiable biological prerequisite for actually delivering omega-3s across the cellular threshold. To prove this delivery works, practitioners and patients need to objectively verify their cellular incorporation. For decades, modern cardiology and general practice have relied almost exclusively on standard lipid panels, specifically cholesterol tests, to assess heart health. Yet this legacy model contains a critical diagnostic failure. Approximately 50% of sudden myocardial infarctions occur in patients who have perfectly normal cholesterol levels. The massive longitudinal Framingham Heart Study exposed the true scale of this diagnostic blind spot. When researchers reviewed generations of data, they found that standard cholesterol levels failed to accurately predict major adverse health outcomes, including the risk of sudden cardiac death. Cholesterol is a volatile metric. The reading can be heavily skewed by the specific meals a patient ate just days prior to the blood draw. A cholesterol test merely measures circulating lipid traffic in the bloodstream. It completely fails to measure the actual structural integrity of the heart's cellular architecture. To predict these outcomes accurately, clinicians require a superior diagnostic tool, the Omega-3 index. Rather than measuring circulating traffic, the Omega-3 index measures the exact percentage of EPA and DHA that has successfully integrated, specifically, into the membranes of red blood cells. Because human red blood cells have a definitive 120-day life cycle, this measurement cannot be skewed by a single meal. It provides an incorruptible 4-month historical record of lipid incorporation. This chart visualizes clinical risk. When a patient's omega-3 index drops below 4%, they enter the highest risk category for sudden cardiac death. The target is an index above 8%, where patients show a 90% reduction in sudden cardiac death risk. Utilizing a true test-based nutritional protocol allows practitioners to objectively track a patient's cellular architecture, watching them transition from the danger zone to the optimal zone over a single 120-day cycle. Globally, over 1.5 million of these tests have been administered, and 97% of people fail their initial baseline. True preventative health requires abandoning volatile lipid isolates and outdated blood metrics. It demands molecularly stable protocols, verified by rigorous cellular indexing.